Good evening. This is Dr. John Bennett broadcasting from sunny and dark Miami. It's 8 p.m. Eastern Standard Time. Tonight we have the pleasure of having Sina Pourghodrat. He's a biomedical engineer from Nebraska. He's a cornhusker. And tonight he's going to talk about electro-hydraulic surgical tools, small enough to widen the scope of minimally invasive surgery. And this is from an article that was posted on MedGadget. Good evening, Sina.
Good evening. Thank you for having me today.
Yes, Sina, and thanks for coming out. I tell you what, let me just show the audience. I want to show the audience something. It's a tweet board, which I want to encourage people to use. Just a second here.
Sure.
Okay, because we're trying to get, people to actively participate in the Hangout. Okay, for anyone watching, okay, this is the page on MedGadget. It's right on the front page. This is where the screen is at. Now, as you can see, there's a tweet board there. You simply compose a tweet. You just give permission for Twubs, that's the platform, to use your Twitter account, or you can use the hashtag MedGadgetTV to come into the Hangout. And, we'll have a time period. We'll see if you have any questions or comments. Okay, why don't we start off, Sina? Just tell us a little bit about your background, how you got into biomedical engineering and where. And why don't we start off with that?
Sure. So I got my bachelor degree in mechanical engineering and also my master's degree in mechanical engineering. And then I was looking for real problems, rewarding research to perform. And then I realized that in biomedical engineering, there are a lot of unmet needs and then a lot of challenges that need to be tackled. So that's why I chose biomedical engineering, and I got my PhD in biomedical engineering, and I worked with a center called Center for Advanced Surgical Technology at the University of Nebraska Medical Center.
Well, did you first go into engineering and then decide, well, I'm going to go to biomedical engineering, or you have to pick biomedical right away?
No, I had to first get my degree in mechanical engineering, and then I switched to biomedical engineering.
Okay, very good. Okay, why don't you tell us about your work?
Sure. So basically back at CAS, Center for Advanced Surgical Technology, I did several projects all around medical robotics, surgical robotics for minimally invasive surgery. And then the main project I worked on was a robot for natural orifice surgery. And so the main issue to tackle there was to create a robot that is small enough to go inside the body and then perform abdominal surgery. So it was an in vivo application of a robot. So when it comes to in vivo application, in vivo robotics, there are a lot of challenges just because of the environment of the human body. So the first challenge was to make the robot very small so that it can go inside the body. And then at the same time, the robot has to be fast and powerful enough to react to the surgeon's input in real time and then be able to perform a procedure. And one of the big barriers in robotics for natural orifice surgery was actually the lack of tool exchange while the robot is inside the body. So there was a need to create a multiple instrument manipulator for the robot such that when the surgeon is trying to perform the procedure and he or she needs to exchange instrument, use different instruments to perform the surgery, there was nothing before that. So the challenge was to create something that can carry different instruments. But previously, researchers had tried to create like motor-driven manipulator But the problem with motors, electric motors, is that they're slow and they are not compatible with the human body. And then at the same time, they're still bulky because with motors, you want to have high power, you want to have high speed. And then by nature, electric motors are not good for like miniature applications. So then we decided to switch to fluid power, such as hydraulic, pneumatic, to create a multiple instrument, a cartridge that is capable of carrying 4 different surgical instruments. So that's where we created an electro-hydraulic manipulator that is capable of carrying 4 different instruments, and it's small enough and fast enough to perform surgical procedures.
Let me just comment on one thing. The definition of robot, because I think most people think when you say robotic surgery, they think of a robot with 2 arms, 2 legs. But in truth, isn't it any mechanized device? Could you please define robot?
Sure. The robot would be a device that actually has some sort of electromechanical components to it, and then it allows the surgeon or the user to perform a task more precisely with higher dexterity. So okay. That's where medical robotics come to play.
Okay, very good. Okay.
Sure. So I created an electro-hydraulic multiple instrument cartridge that is capable of carrying 4 different surgical instruments. And then at the same time, it's half the size of the electric motor driven version. And then it's much faster and it's capable of providing enough force to manipulate tissues, to cut tissues and perform surgery. And also there was no electronic, like no onboard electronics. So I devised a control mechanism, a control method that allows all of the electronic to be placed outside of the body, ex vivo, and just the manipulator and all of the surgical tools to be inside the body. So that was a huge difference between electro-hydraulic cartridge that I created with the previous motor-driven manipulator. So, in medical device field, FDA clearance is a big deal. So eventually what you create has to actually be cleared by FDA. And then when it comes to FDA approval, EMC, electromagnetic effect is very important. Electromagnetic interface also is very important. So with onboard electronics, onboard motors, it's really difficult to sterilize the motor and then also go around all of the issues that are created by electronics and onboard motors. Mm-hmm. So that was also a huge benefit of using hydraulic or electro-hydraulic manipulator as opposed to the electric motor version of it.
Mm-hmm. Okay, do you want to show us some slides?
Sure. So
very good. Outline.
Yeah, so basically back at CAST, I worked on several projects and all of them were around replacing electric motors, miniature electric motors with fluid power. And so I worked on 2 projects. One of them was the robot for natural orifice surgery. And then the other one was a robot for colonoscopy. And both of them were fluid powered, no motors, no onboard electronics. And I'm gonna go down to the project to the slide that actually shows the manipulator. So here it is. Yeah, so as you can see here, this is the manipulator that is intended to attach to the robot, to the tip of the robot, and it's capable of carrying 4 different instruments. As you can see here, there are 4 holes here, and then different instrument can come out of this cartridge. And so the OD, the outer diameter of this cartridge is about 14 millimeters, which is small enough to go inside the body. And then the length was about 55 millimeters, which is, again, small enough for in vivo application. And then let me show you a picture of the robot, if I have it here.
When you say small instruments, probes, what kind of instruments?
So there are actually laparoscopic instruments. One of them is a grasper. The other one is scissors.
Okay.
And then other instruments can be used.
Okay.
These small instruments were very small, 2 millimeters OD.
Right.
And
I can see the scissors. Yeah, at the bottom there. They're there for cutting, obviously.
Sure.
Micro scissors.
Right.
Okay.
And then, yeah, I don't think I have a picture of the robot here, but let me find it somewhere. Do you still see my slides okay?
I see the fluidic rotary outline. You're on the outline, the first page now, outline.
Okay, I want to switch to the website so that you can see.
Okay. You know, there's a robotic surgeon nearby that I would have loved to have had on this program. Robert Smith, he's a surgeon from Naples.
Cool.
Great.
He
works, you've heard of Da Vinci, right? He works for Da Vinci.
Sure. So actually this picture shows an overview of the snake robot for natural orifice surgery. As you can see, this is the snake part of it. And then there is a bimanual arm that is attached to the snake part. And then the multiple instrument that I created will go right here on the tip of the robot. And then, as I mentioned, it's capable of carrying 4 different instruments, each for each arm. And then because you have 2 arms, you will have 8 surgical instruments ready at the site of the surgery to be used. And then that's enough for most of the natural orifice procedures. And as I mentioned, this manipulator do not have any electronics whatsoever, no electronics on board. And then they're small, very small, they're fast, and then they're powerful.
Mm-hmm.
And then also, let me talk a little bit about the other project that I worked on.
Sure.
And that project is also a very interesting and challenging project as well.
Fluidic rotary actuator, colonoscopy, okay?
Right, yeah. So the other project I worked on was a miniature flexible robot for colonoscopy. As you know, colonoscopy is a procedure that has a lot of issues. Traditional colonoscopy has a lot of issues. The main issue in colonoscopy is loop formation. That is the main cause of bleeding, tissue perforation, and also the chance of transmitting disease from one person to another person.
Yeah.
And you can see actually so here in this picture, you can see how a loop can form when the gastroenterologist is trying to push the colonoscope inside the colon.
Right. Well, a lot of people don't have it because it's so uncomfortable. So this would be a smaller probe?
Right, right. So the whole research is actually trying to make the colonoscopy procedure more convenient, more comfortable,
Right.
and then also try to somehow automate the whole procedure so it can actually meet the need of mass screening for the patients.
Yeah, most men don't have it because it's so darn uncomfortable.
Right, right. So what we did actually here was to create a flexible, soft, and disposable robot that is self-propelling and self-steering for the colonoscopy. So previously, researchers actually have tried to develop robotic systems for colonoscopy, but most of them are using either inchworm techniques or legged robots, as you can see here. So this is a legged robot, and this is an inchworm robot for colonoscopy. But you don't want this to be inside your colon, right? And then also like this type of
the gerbil.
right. And then also this technique is very slow, and then also because it sucks the tissue, it's not also safe to interact with the colon. So we came up with a novel method to develop the robot. So this is the very early generation of the robot. So it has a head, it has just a flexible tube, and then an introducer or holder. And so it improved, the robotic design actually improved until we got to something like this. And we tested the robot and it showed very promising results. So this is a picture of the robot going through a long tube. So it has a head and then also a very flexible, it's more like a balloon, like a tube, flexible tube that goes inside the colon. So it's very safe, it's disposable, it's very fast, and then semi-autonomous. So we tested the robot without any external control. The robot was capable of going through a simulated test setup, as you can see here, through a synthetic colon, all the way from the beginning to the end with sharp ends, as you can see. So there was no need for an external person to somehow maneuver or push the robot inside. And then the robot will go all the way from the beginning, the anus, to the cecum of the colon with no external manipulation or even discomfort to the to the patient.
Do you do this on animals at all? Or have you tried it, or just tubes?
So we tested on animal as well. So we actually did initial animal testing, but it was somehow successful, but not fully successful because the animal was not prepared according to real colonoscopy procedure.
Yeah.
So, but this is an ongoing project, ongoing, as I said, research, and we are trying to add a camera to the tip of the robot right here, and then also we'll do more animal testing.
Mm-hmm.
Yeah, so if you have any other questions, I'll be happy to answer.
Okay, well, obviously, have you tried taking biopsies and things? I know that first you got to establish whether it can move okay, but then you've got to start thinking about, taking biopsies. And that's probably one of the tools on the machine, correct? On the robot is a biopsy taker?
Right, right. As I mentioned before, it's a very early stage project.
Oh, okay,
So
okay, yeah, I thought so.
Right. In colonoscopy, actually in robotic colonoscopy, one of the main challenges is the locomotion. As I mentioned before, previous locomotion method, they use legged robots or inchworm robotic method, which is slow and then it's not safe to interact with human tissue. So the main challenge was to come up with a novel, safe, and flexible locomotion method. And that's why we first focused on coming up with a good locomotion method. And then we tested that locomotion method. It worked very, very well. And then the next step is to add actually a camera to the tip of the robot so that you can examine the colon. And then that could be also, just for screening. And then if you need to do a biopsy or get some tissue samples, the next step would be to add a channel to the robot and then be able to pass a tool such as a grasper or other tools to perform surgery or to remove cancerous tissues.
Okay, very good. Now, just to reiterate, you said, is the advantage of this being a hydraulic system as opposed to electric is purely FDA reasons? Like FDA does not have to approve, doesn't put you through such rigorous trials for hydraulic system as opposed to electric. Am I getting that right?
That's one of the main reasons, but there are other big players, big factors. So as I mentioned before, with miniature motors, with miniature electric motors, there comes a trade-off between the size of the motor and then the load capability, capacity, and the speed of the motor. So usually small motors are not that fast, and then they're not capable of providing enough force or torque to perform these surgical procedures.
Yeah.
So that's one issue. The other issue with them is, as I mentioned, the size. So usually they're still big and bulky because you need gear head and other stuff to add to the motor to actually design the robot. And then also there's always a chance of electric current to be transmitted to human tissue, so that's not safe.
Right.
And yeah, so these are the main issues with electric motors that actually was a motivation for us to think of other methods.
Okay. And this is a project you're working on now, colonoscopy.
Right. This is the project that I worked on when I was working for University of Nebraska.
Okay. Is this university funded, or are you getting outside funds, or?
Yeah, back at the University of Nebraska, these projects that I worked on were funded by NASA, NIH, and local state agencies.
NASA?
Right, yeah.
Wow. I didn't realize they fund scientific projects.
They do.
Okay. Okay. Do you have any more slides to show, or?
Sure, I do have some slides to show regarding the other project I worked on.
Sure.
So basically, after successful testing of the electro-hydraulic manipulator, we said, what if we make the whole robot driven by fluid power? So we started to design a robotic arm, just a robotic arm, to see if we can use hydraulic or pneumatic to move these joints. And then the next thing was, off the shelf, there was no small cylinders, no small linear or rotary actuator. So we had to come up with novel designs, novel approaches to create linear and rotary actuators. So I invented two actuators. One was a linear actuator, and then the other one was a rotary actuator, as you can see pictures of them here. So these actuators are very small, and then also they're leak-free. They're easy to manufacture, very inexpensive compared to, again, like electric motors or electric actuators. And I tried to use these actuators and the electro-hydraulic manipulator to create a robotic arm. So two of this arm could be put together to create a bimanual arm that could be attached to the snake robot, or it could be a standalone robot for single site surgery, for laparoscopic single site surgery, or natural orifice surgery.
Now, you must have to make these little pieces, right? You don't go to the hardware store and buy them. How do you get these little pieces? You have to make them yourself?
Yeah. So as I mentioned, these actuators are very easy to manufacture. If you have just a 3D printer in your center.
Oh, wow.
3D printer, like it's called rapid prototyping skills. So we had a 3D printer and also a laser cutting machine. So we designed these parts with SolidWorks and then used 3D printer and laser cut machines to create these small actuators, and then just assemble them together and made the whole robotic arm.
Wow. You know, that's one influence of 3D printers I never even thought about. It's the manufacture of micro pieces of robotic surgery. That's amazing. It's being used for that. Wow.
That's correct. That's actually 3D printers had speeded up the whole process of creating small parts, small robotic parts.
Wow. That must make it easy. You don't have to wait to order a part or whatever. You can make it yourself.
That's correct.
It seems like there'd be a lot of. Do you use a microscope to put these together? You must have to, correct?
Yes, we did have a microscope and then other small tools to be able to.
And you have to manipulate it. You can't really drink too much coffee before you do that, right? No, that's a fact, because I know when we scrubbed in hand surgery under the microscope, you could tell if you had a slight tremor from coffee or whatever.
Yeah, some parts actually, as you can see here, some parts such as these very small bearings and then some other small pins, I had to really focus and then use microscope to be able to put them together. But other parts were not that small. Like this parts were not really that small. The OD is about 15 millimeters, say half an inch to, yeah, it was about half an inch. So these parts are not very small, but the parts inside the actuator, as you can see here, the pin, this part, the bearing, these are very small. Like this ball bearing, the OD was about 2 millimeters, which is very small. Mm-hmm. And the shaft here was about 2 millimeter again, or no, even it was 1 millimeter. So very small parts to assemble.
Yeah, it doesn't look easy. And what's the type of 3D printer you use in the lab?
I believe it was Object Pro, if I'm not mistaken.
Is that a pretty commonly used 3D printer in laboratories?
It is. Yes, it is.
Okay.
And let me also show you one other parts that I created. So this picture shows electric motor driven robotic arms. Actually, it's the whole robot for laparoscopic single site surgery. Mm-hmm. And as you can see on the tip of the robot, you see a grasper here. And then you see that this part is bulky and big. So because it uses two electric motors to drive, to open and close the grasper, and then also rotate the grasper. So on the same line, we said, what if we drive, or what if we actuate this grasper hydraulically or pneumatically. So we started to think about methods or ways of doing this. And then you see here that we created several prototypes, and eventually we got to this prototype. And then it's really small again, and then it doesn't have any motors or anything. It just a tube goes to the grasper, and then with pressurized air, you can open it up, and then there's a spring to close it back. Then also we tested the grasper. It was capable of providing enough force, about 3 Newton, for manipulating or cutting or holding onto tissues. And it was pretty fast. As you can see, open and closure time was less than 1 second. But with electric motors, it's very difficult to get that fast actuation.
Well, you know, I can see how your background in mechanical engineering would help in things like this.
That is actually what I use a lot. So all of my backgrounds in 3D design, in manufacturing, in prototyping, as well as testing, it helped a lot.
Was 3D printing part of your mechanical engineering education?
Yes.
It was. Wow. So it's mainstream now in education, 3D printing.
Correct.
Wow. Things have changed.
Yes, yes. Like I said, a few years ago, we did not have 3D printer in the lab, and then also we did not have a laser cutting machine. Yeah. So we had to design and then also have an external machine shop or external vendor to manufacture or make the parts for us. It was costly, it'll take time. And then sometimes when it comes to miniature parts, they're not actually capable of doing this type of works by traditional manufacturing equipment.
Well, it sounds like development of 3D and laser is accelerating innovation in biomechanical engineering.
Yes, yes, it is.
Okay.
Yeah, so to summarize the project I worked on, the problem definition was how to further miniaturize the current robotic systems to the size that can be inserted inside the body, and then at the same time, we're not compromise the speed or the load capability of the robot, and then we're gonna make it much faster and more powerful. So that was a very challenging project. And also the other part of the challenge was how to create a cartridge that is capable of carrying several instruments. So tool exchange would be not a problem anymore for natural orifice surgery, because natural orifice surgery, when you put the robot inside the body and then you need to use a different instrument, you don't want to pull the whole robot outside, change the instrument, put it back, and then use it. And then that has to happen several times, because in many procedures, you need at least 8 to 9 different instruments.
Right.
So that was another challenges. And as I mentioned before, the other challenge was how to minimize the electronics, the onboard electronics or onboard motors, so the robot will be safer, and there would be no concern regarding EMC, electromagnetic interference, or electromagnetic compatibility. So combining all of this issue, we came up with a novel control methodology to put all of the electronics outside of the body, such that there would be no onboard electronics, no onboard motor. And then also we invented two different actuators, a linear and a rotary actuator, and then also an electro-hydraulic multifunctional manipulator to be attached to the tip of the robot for the natural orifice surgery robot. And then on the other project, we use all of these concepts. We applied some parts that we actually created in order to create a different robot for colonoscopy. And then the challenges were almost the same. The robot needed to be small, needed to be safe, flexible, soft. And then in addition to that, we wanted to create a semi-autonomous robot such that with a push of a button, the robot can, when the robot is entered into the colon, it can actually explore the whole length of the colon from anus all the way to cecum with minimal external control or minimal external manipulation. So that was the whole purpose or the whole goal of the colonoscopy project.
Very good. Okay, Sina, you can get off the screen share. Just click on the green arrow before we close here.
Sure.
There you go. Just click on that green button again and get off the screen share. There you go. Okay. Well, one last question, and maybe I missed it, but this instrumentation is not, of course, it goes directly into orifices, like you mentioned, but it also goes inside, like a laparoscope?
Yes,
or strictly into the orifices?
So, like, we created two different types of robots. One was for natural orifice surgery, and then the other one was for laparoscopic single site surgery.
Right. So you can use it for both.
Right.
Okay. Yeah, that's pretty that's good. That's pretty versatile. And I'd love to get a surgeon on here with you to ask you questions, because they're a lot more versed in these things than I would be. But anyways, it's good to go inside your world and what you're doing, the exciting stuff you're doing with mechanics. And I was very surprised to hear that 3D is impacting instrumentation so much. And that's part of our education. A lot of dynamic things going on.
Sure. So, yeah, the 3D printer and the whole rapid prototyping is really helpful in creating things fast, and also it facilitates the try and error that usually is needed for creating novel and small things.
Okay, Sina, and so if someone wants to get a hold of you, just Sina Pourghodrat at the University of Nebraska, correct?
That is correct. And then yes, that would be one method, and the other method would be my email, which is my last name Pourghodrat, POURGHODRAT @gmail.com.
Okay, I'm sure they could Google it and Google your article that you have in MedGadget, and this hangout will be on MedGadget also. So we'll keep up with your developments and keep on working. Thank you very much.
Thank you.